Okay, in my first talk today, I want to talk about the dangerous beauty of bookmark lookups in SQL Server. Who of you has already an idea what a bookmark lookup in SQL Server is? Okay. Who of you has already attended a session of mine yesterday? Okay, so I don't introduce myself anymore. You already know everything that you should know about me. What's the agenda for the next 90 minutes? The first step, I want to talk what a bookmark lookup is in SQL Server, why SQL Server needs a bookmark lookup so that everyone has a common understanding about bookmark lookups, and then I just want to show you different problems that can occur in SQL Server in combination with execution plans that contains bookmark lookups. We will talk in detail about the so-called tipping point, about a problem in SQL Server called parameter sniffing, inaccurate statistics, how SQL Server deals with parameterization in combination with bookmark lookups, and in the end, if time permits, I also want to talk about some specific kinds of deadlocks that can also occur in SQL Server in combination with bookmark lookups. So mainly, I'm just talking about the various problems that bookmark lookups can have in SQL Server. A bookmark lookup means that the query optimizer has chosen in the execution plan a non-clustered index, means we are reading the requested data from that non-clustered index, and finally we retrieve in our select list additional columns that are not part of that non-clustered index. Means we get some records from that non-clustered index, and afterwards SQL Server has to retrieve the additional requested columns for every record that we have retrieved from that non-clustered index. And when we look here at the execution plan, you will see that SQL Server performs here a bookmark lookup operation. Means for every record that we retrieve from that non-clustered index, SQL Server accesses our table, our clustered index, or our heap table, and just retrieves the additional information. When we deal with a bookmark lookup, we have two kinds of bookmark lookups in SQL Server. We have a so-called clustered key lookup. That kind of bookmark lookup is performed by SQL Server when we deal with a clustered table, so a table with a clustered index. If we deal with a heap table, a table without any clustered index, then we have a so-called row identifier lookup in our execution plan. As we will see later, we can eliminate bookmark lookups very easily in SQL Server by creating a so-called covering index. A covering index in SQL Server is just a traditional non-clustered index which contains all the columns that we are requesting in our query. So normally when you have a query in front of you, you should add the columns on which you are restricting in your where clause into the navigation structure of that non-clustered index so that you can perform seek operations, and every additional column that you are referencing in your select list, you should include in the leaf level of that non-clustered index. Means when we are including those additional columns in the leaf level of the non-clustered index, we can eliminate that bookmark lookup in the execution plan. Of course, when we include additional columns in the non-clustered index, we just create a redundancy of that data. Means those columns are part of our table, of our heap table or clustered table, and those columns are also part of that non-clustered index. Means when we are changing that column, we are degrading our write performance because SQL Server has to change that column twice. Once in our table and also once in the non-clustered index that we have created previously. That's also the problem of indexing. On one hand, you're improving your read performance, and on the other hand, you're just degrading your write performance. Let's have a look on that. I have here a simple query which retrieves the record with the database log ID of 15. It's a heap table, a table without a clustered index. As you can see, we have on the column database log ID a non-clustered index. That non-clustered index is referenced in the execution plan, so SQL Server makes a seek operation on that database log ID column, as we can see from the seek predicate. And the problem that we have now with that query, we select the column database log ID and also the column database user. That column database user is not part of that non-clustered index, means SQL Server has to perform a lookup operation on our heap table. And as you can see from the output list, we request here the column database user. Means from the execution plan, a bookmark lookup is always performed with a nested loop operator. Means for every record that we get from our non-clustered index, SQL Server has to perform that bookmark lookup into our table. Means the more and more records that predicate returns you, the more often you have to perform that bookmark lookup. In that case, we just return one row, means we also have to perform that bookmark lookup just once, as you can see here from the number of executions. I have here another query which performs a bookmark lookup on a clustered table. As you can see, we request here a range of email addresses from the table person.email address. As you can see, that seek operation returns us 19 qualifying rows. In addition, we want to request the column modified date. The column modified date is not part of that non-clustered index, means for every row that we are returning from that seek operation, SQL Server has to perform that key lookup on our clustered table. Means we execute that bookmark lookup 19 times for every row that we return from the index seek operation. You can see again from the output list, we request the column modified date. As you can see, for that simple query, we already need 42 logical reads. Means SQL Server read here 42 pages of 8 kilobytes. Another query, just the same thing. We return 8 records. In that case, we perform that bookmark lookup 8 times, number of executions. We have here 18 logical reads. As I've said previously, such a bookmark lookup in an execution plan can be eliminated very, very easily. You can see that we retrieve the column modified date with the bookmark lookup, means we can create an additional non-clustered index which includes that column modified date in the leaf level of that non-clustered index. Means when we create that non-clustered index, SQL Server is finally able to satisfy the complete query from that non-clustered index. Means we're just eliminating that bookmark lookup. So let's create that one. Okay. Let's create that one. When we finally rerun our query again, you can see SQL Server has chosen that newly created non-clustered index. So there's no need anymore to perform that bookmark lookup, because every column that we're referencing in our query is now part of that non-clustered index. Means in that case, we have only 2 logical reads instead of 18 logical reads. So that's already a huge difference.
Was that the table with the clustered index?
Yeah.
So it chose to use that. Okay, so
Yeah.
chose to use the non-clustered
Yeah.
index.
In that case, Query Optimizer has seen, hey, every column that you are referencing in that query is part of that non-clustered index, so we just read that data from the non-clustered index. Of course, when we update that column modified date very, very often, that non-clustered index just degrades our write performance. Because now when you're changing that column, you also have to change that column twice. Once in the clustered index in our table and once in the non-clustered index. So when we run here a simple transaction and we say update person address set modified date equals get date where address ID equals 42, and we run that transaction, and when we look at the execution plan, you can see we have a clustered index update operation, and SQL Server also has to update the non-clustered that we have created previously. Because with the included column, we just have created redundant data in that table. We are storing that column modified date physically 2 times. Once in the clustered index, once in the non-clustered index. So as you can see here, we need for that query 4 logical reads. When we drop again that non-clustered index and we run the update query again, it will be faster. No, not really. It's just a small table. But when we look at the execution plan, no, this was the wrong one. This one. So now we should be faster. Yeah. Now we just have 2 logical reads, so our write query is just faster. As you can see, we are just updating our clustered index, no non-clustered index. Of course, our read query or select statement is again slow. That's the problem of indexing. On one side, you're increasing your read performance, on the other hand, you're degrading your write performance. Means you have to find a good middle way how you index your databases.
So that example you just used, if it was a clustered table or a non-clustered table?
This was a clustered table with a clustered index.
Right, so if it was a non-clustered table and it didn't cover...
The non-clustered index that we had previously didn't cover the query. Therefore, SQL Server introduced the bookmark lookup.
Yeah, so if you then added the non-clustered index, that includes the new column.
Yeah.
Is there any performance difference between it being originally a clustered table or a non-clustered table?
The non-clustered is just smaller. Because you just include in the non-clustered index a subset of your columns. Means the non-clustered is just smaller and therefore faster. Therefore the query optimizer also has chosen the non-clustered index. Makes sense? For example, when we recreate that non-clustered index, when we run our query, SQL Server uses it. We have just 2 logical reads. When we hint SQL Server for our clustered index with the index ID of 1 and we run that query, you are scanning your complete clustered index, and in that case you have 348 logical reads. Means the accessing the clustered index is just more expensive because the clustered index is your complete table. In that case, we have read our complete table.
Is this related somewhat to poorly performing plans? Because presumably it's going to do the lookup if it thinks there's so few rows.
Yeah, that it makes sense. Yeah.
Do them one by one.
Yeah.
As opposed to the clustered C.
Yeah.
When it knows there's a hell of a lot more.
Yeah. And now the fun begins. That was just an introduction, so that we have a common understanding about bookmark lookups. Of course, a bookmark lookup only makes sense when you're expecting a small number of rows. Imagine you have a table, let's say, with 100,000 records. When you just expect a few records from that table, it makes sense to make that bookmark lookup a few times. Imagine from that table with 100,000 records, you're expecting all rows. It wouldn't make sense to make that bookmark lookup 100,000 times. Because in that case, the complete scan of the clustered index would be faster. And that point where SQL Server decides if we perform a bookmark lookup in our execution plan or a complete clustered index scan is the so-called tipping point in SQL Server. Based on our statistics, on the estimation, SQL Server decides if the query optimizer generates us a bookmark lookup plan or a plan with a complete clustered index. And the most important thing here is it's based on the estimation, based on our statistics. Means when the statistics are telling you you are estimating for a state province ID of 42, one row, the query optimizer generates you an execution plan with a bookmark lookup. When you in reality return 100,000 rows, you have a huge performance problem because SQL Server just takes that plan and executes it. The tipping point itself depends on the number of pages that we are reading. Means the tipping point doesn't care about the number of records. And as you can see here, SQL Server chooses a plan with a bookmark lookup when we read around 1/4 to 1/3 of our pages of that table. When you're reading more, the query tips over and SQL Server generates you a plan with a complete clustered index scan. Means it doesn't matter how many records you have in your table. It only matters how large your records are. Imagine we have a table with 80,000 records. Every record is 4,000 bytes long. In that case, we can fit 2 records of 4,000 bytes on one page of 8 kilobytes. Means the tipping point is somewhere between 12 and 17% of those records. When you have the same table again with the same amount of records, 80,000 records, but every record is only 40 bytes long, then you can fit 200 records on one page of 8 kilobytes, and then your tipping point is somewhere between 0.12% and 0.17%. Means your non-clustered index, which isn't a covering non-clustered index, is almost useless. In that case, you can only read around 160 records out of 80,000 records with that non-clustered index because of the bookmark lookup. Just think about that. Means the query optimizer will normally not really choose that non-clustered index because accessing that non-clustered index in combination with a bookmark lookup doesn't really make sense. Let's have a look on that. I create here a new table. Every record in that table is 400 bytes long, means we can store on one page of 8 kilobytes 20 records. I create on the first column customer ID a unique clustered index, and I insert 80,000 records in a while loop into that table. Means every record is 400 bytes long, we can store 20 records on one page of 8 kilobytes, means we have in the leaf level of that clustered index 4,000 pages. Takes a few more seconds. And afterwards we create on the column value a non-clustered index. Means when we restrict on that column, when we retrieve additional columns in the select list, we just generate a bookmark lookup in the execution plan. When we read from that table everything, SQL Server chooses a clustered index scan operator in the execution plan. Means we're just scanning every page of that leaf level, and we have here a little bit more than 4,000 page reads. We have now 4,000 pages, means the tipping point is somewhere between 1/4 and 1/3 of those pages, so between 1,000 and 1,333. We have 80,000 records in that table, means our tipping point is somewhere between 1.25 1.7%. Means in that range, up to that range, SQL Server will choose in the execution plan a bookmark lookup because it's faster. When we are over that range, the query dips over, and the query optimizer gives us an execution plan with a clustered index scan where we have a predicate to filter out non-qualifying rows. I'm running here now a simple query. Customers were values smaller than 1062. When we look at the execution plan, we have a nice bookmark lookup. Means that non-clustered index seek operator returns us 1061 rows. Means for every record that we return, we have to perform that bookmark lookup, number of executions. We perform here a bookmark lookup into a clustered table, means for every record, SQL Server has to perform a seek operation through 3 levels to find the row in the clustered index. Means every bookmark lookup here on the clustered table costs you 3 logical reads, because you have to perform a seek operation into that clustered index with 3 levels. And as you can see, that query already costs you 3,262 logical reads to retrieve 1,061 rows out of 80,000. When you make a complete scan of the clustered index and retrieve all 80,000 rows, we had just 4,016 page reads. Just think about that. At some point in time, that bookmark lookup doesn't really make sense anymore, because it just costs you too much. And what I'm doing in the next step, I'm just retrieving one additional record. Whoops, one more. And now, as you can see, our bookmark lookup is gone. Means the query optimizer ignores your non-clustered index because you are not retrieving a very selective result anymore. In that case, it's more efficient to scan the complete clustered index and discard with a predicate non-qualifying rows to get back to your 4,016 logical reads. Okay? Imagine now, we have a plan with a bookmark lookup, let's say with a parameter value. That plan gets cached, and afterwards the plan gets reused. Imagine you are retrieving all your customers from Austria, one crazy guy like me. You cache that plan, and afterwards you reuse that execution plan to retrieve all your customers from the UK. You're doing that bookmark lookup over and over and over and over again, and your performance will just suffer. We'll see that later. I create here another table. In that table definition, every record has a size of 40 bytes. Means when we now insert again our 80,000 records, we can store 200 records on one page of 8 kilobytes. So we are dealing with the same set of records, 80,000 records, but instead of 400 bytes, every record is just 40 bytes long. Means the tipping point comes much earlier. I create again the same non-clustered index on the column value. When we retrieve the complete table data, we have the clustered index scan. Clustered index scan costs you 419 logical reads. With a table with 400 pages, means tipping point is somewhere between 100 and 133 pages. Again, same 80,000 records, means tipping point is somewhere between 0.12, 0.17% of the records of that table. Means you can't retrieve too many records with that non-clustered index anymore. I have a simple query, 156 records, we have a bookmark lookup. As you can see, the bookmark lookup for retrieving 156 records costs you 332 logical reads. Retrieving all 80,000 rows costs you 419 logical reads. Just think about that. Let's retrieve a few more records. Now we have a clustered index scan. Again with a predicate. And we are back to our 419 logical reads. Imagine that now. You have on that column value a non-clustered index, but the query optimizer doesn't use it. It doesn't make sense because performing that bookmark lookup over and over and over again just costs you too much. So a non-clustered index, which isn't a covering non-clustered index, has a very, very selective use case in SQL Server, especially then when you're dealing with very, very small records. And the goal of a good database design should be to have very, very small records. Imagine what happens when we hint SQL Server for that non-clustered index and we retrieve all 80,000 rows through that non-clustered index with a bookmark lookup. As you can see, we are getting now 80,000 rows from that non-clustered index seek, means we have to perform that bookmark lookup over and over and over again 80,000 times. What do you think? How many page reads we have? A lot. 165,000. Just think about that. Now imagine SQL Server just reuses such a cached plan. The performance will just degrade and suffer. And as you can see in the execution plan, that lookup costs you 96%. Of course, when you have here a query like a select star, it's very hard to provide here a covering non-clustered index, because in that case you have to include every column in the leaf level of that non-clustered, means you are mainly duplicating your table data. Doesn't really make sense. When you just read your data from the clustered index, you would have almost the same performance. Okay? Questions on that so far? Okay, let's move on. Let's talk now a little bit more in detail how SQL Server caches execution plans and what can happen when we just reuse a badly cached execution plan with a bookmark lookup. Imagine we have a stored procedure, you have an input parameter, like a country, and you just retrieve rows from a specific country. Like all your customers from Austria, a very, very selective result. You have just a few customers in Austria. You have on that country column a non-clustered index, means SQL Server uses that non-clustered index, introduces in the execution plan a bookmark lookup. The problem that we have, SQL Server caches that execution plan, and when you rerun that stored procedure with a different input parameter again, then SQL Server will just reuse that cached plan. Means when you afterwards run that stored procedure to retrieve all your customers from the UK, you get back a huge amount of customers. Then SQL Server just reuses that cached plan with the bookmark lookup and performs the bookmark lookup over and over and over again. Means your performance will just suffer. That's the so-called parameter sniffing problem. Microsoft says it's a feature, we say it's a problem or bug. Means when you have parameter values in a stored procedure, you always have a so-called compile time value and a runtime value. Means your execution plan is compiled and optimized for a specific value, and afterwards you are running that cached plan maybe with a different runtime value. Means in combination with bookmark lookups, you will get a huge amount of performance problems. You will see a very, very high IO consumption. We've already seen earlier when we retrieve all 80,000 rows with a bookmark lookup, we have 165,000 logic reads. The nested loop operator in the execution plan is CPU bound, means your CPUs will also go up. Means, as a conclusion, you just have a really, really badly performing SQL Server. I've already seen plans with the bookmark lookups where the whole SQL Server just got crazy. Your CPUs are going up to 100%, and maybe you are reading 10 gigabytes, maybe you are reading 100 gigabytes of data from your storage just because of that bookmark lookup. Because you're doing that bookmark lookup for every row that you return from the non-clustered index. We have here now different options how we can work with that specific problem. SQL Server provides us here multiple query hints. We can perform a recompilation of the complete stored procedure. Since SQL Server 2005, we can also make a so-called statement level recompilation. Means we just recompile that specific statement within our stored procedure. Means every time when we execute that stored procedure, SQL Server gives us a new execution plan which is optimized for the current provided input parameters. With also a so-called optimize query hint. With that query hint, we can also optimize our execution plan for a specific input parameter. For example, when you know normally I'm executing that stored procedure with an input parameter of UK because I normally retrieve all my customers from UK, then you can also tell SQL Server with that query hint that you always want to have an execution plan which is optimized for the parameter value of UK. Means when you're calling first the stored procedure with an input parameter value for Austria, you will get a plan which is optimized to retrieve all your customers from UK. So maybe you perform a complete scan of that table. Let's have a look on those things. I create here a very simple table, and I just insert into that table 1,500 rows. But when we look into that table, you can see that we have in column 2 an uneven data distribution. we have once the value of 1, and we have 1,499 times the value of 2. You have one customer in Austria, a huge amount of customers in the UK. Just an uneven data distribution. Normally we have in every table an uneven data distribution. Our data is not really distributed normally. So just a common problem. And I create a non-clustered index on that second column. And now I create a very simple start procedure, nothing special here. We have one input parameter value, and we just use that input parameter value to select data from that table. Let's run that start procedure. Value of 1, very, very selective, so in that case it makes sense to perform a bookmark lookup. As you can see, the seek returns 1 row, means we perform the bookmark lookup just once. Very simple. In that case we have 3 logical reads. What happens when we rerun that start procedure? Now SQL Server sees that we have, with the name of that start procedure, already a cached plan, and reuses that cached plan. Means normally plan caching is a very, very good thing in SQL Server, because you don't need to compile every time for a query a new execution plan, because compiling an execution plan takes some time and takes some memory. Now plan caching is a bad thing, because we have just reused that plan with a bookmark lookup. As you can see, the index seek has an estimation of 1 row. For the input parameter value that we initially supplied. Means the plan that we have in front of us is optimized for the processing of 1 row. But in reality we are getting back almost 1,500 rows. Means instead of performing that bookmark lookup just once, we perform that bookmark lookup 1,499 times. Over and over and over again, means our I/O costs are just exploding. Just think about that. A very simple traditional stored procedure. When we look at the execution plan, at the select operator, you can also see that we have a parameter list. We have our parameter value, and for every parameter value you have a compile time value and a runtime value. In our case, that stored procedure, that execution plan, was compiled and optimized for a value of 1, and currently we are running that plan with a value of 2. Means when you have in that specific column an uneven data distribution, in combination with a bookmark lookup, you introduce a huge amount of different programs. Make sense? So the question is how we can deal with that problem. The easiest solution is of course to provide a covering non-clustered index, just to include those additional columns that we are referencing from the bookmark lookup into the leaf level. Of course here it depends how your query looks like. When you have a select star query, when you just retrieve every column, it's not really convenient to add every column into the leaf level of the non-clustered, because you're just duplicating your table data. As we have seen previously, when you're changing that column, you have to change that column at least twice. Once in the clustered index, once in the non-clustered index. One thing that you can do is the following. You use local variables. So we have the input parameter value, and we assign that input parameter value to a local variable, and then in our select statement we just reference that local variable. Means during query optimization, the query optimizer has no idea which value you are providing in that local variable during runtime. Means in that case, the query optimizer can't really produce you a very good execution plan, because during compile time we have no idea which value we are providing here during runtime. So when we run that execution plan again, you can see SQL Server generates us a table scan operator, because we have now an estimation of 750. So around 50% of that table, we are over the dipping point. So the query optimizer has chosen a table scan in combination with a predicate. The question is why we have an estimation of 750. That estimation comes from the statistics. We have for our non-clustered index a statistics object. And inside the statistics object you have a so-called density value, how dense your data is. We have in that column two distinct values. The value of 1 and 2 means 1 divided by 2 distinct values gives you a density value of 0.5. You have 1,500 rows in your table, multiplied by 0.5 equals to 750 rows. So when you work with local variables, then SQL Server just uses that density value to make an estimation how many rows you are returning. So it depends again on your data distribution which execution plan you are getting here. With a density of 0.5, we are here almost always over the dipping point, so the query dips over. SQL Server always generates us here a table scan, and in that case the table scan costs us 4 logical reads. Yeah?
If, let's say we have an application which don't use a stored procedure, we use things like entity framework or dynamic SQL,
yeah.
Do we have still the same problem?
You still have the same problem when you are working with parameterized SQL statements.
Right.
Yeah.
Okay.
So when you say...
half the tools not available to you, because presumably your application is you can't hard code hints, that kind of stuff into the statement
Yeah.
to avoid the situation.
Yeah. So for example, when we go up, and you say, for example, you have here a parameter value, you have the same problem.
Ah, I see.
When you submit that query from your client application, on the first step, SQL Server compiles you an execution plan. Afterwards, you're submitting the same query. Means SQL Server just generates a hash value across that SQL statement. The hash value is still the same because you're just providing a parameter value. Means you're just reusing that cached plan. Same problem. Completely the same problem. We will talk about parameterization later. Yeah. Same problem. Then, yeah?
Will you also, at the appropriate time, be mentioning the tools we can use, where, for example, we're dealing with generated SQL, yeah, or vendor-supplied SQL, stuff that we can't change to SQL statements. We wish to avoid these performance problems.
Yeah.
You're talking about?
Yeah.
Yeah.
The nice thing about SQL Server is you can also ask SQL Server if you have that specific problem. For every cached execution plan, we have so-called query statistics in SQL Server. So for every cached plan, SQL Server stores statistics how that execution plan performed. As you can see here, we have the creation time of that execution plan, the last execution, how often we have executed that plan, how long you have spent on your CPU activity, you have your physical reads, you have your logical writes, and you also have your logical reads. Means you can do an order by max logical reads minus min logical reads to see where you have a very, very large variation. Just think about that. When we do here an order by max logical reads minus min logical reads. As you can see here, when you have a very, very large variation, then you also should look on these specific execution plans. Just think about that. So you can also read that from the query statistics if you have maybe a problem. In that case, we have here one execution plan. At the minimum, that plan produced 2,361 logical reads, and once in time, the complete same plan produced for 38,000 logical reads. So in that case, you can further dig into that plan. We have here a plan handle, it's a hex value which uniquely identifies that execution plan. Means with the dynamic management function system exec query plan, we can retrieve that plan and further look on that plan what happens here. Okay? So you can also go proactively to SQL Server and ask SQL Server, hey, what are those queries where I have a very large variation between my logical reads? And maybe you have here that parameter sniffing problem in combination with a bookmark lookup.
So sorry, on the select all from table to at cultivar, so the local variable in the storage.
Yeah, that's a local variable. So we have the input parameter, and we just assign that to the local variable.
So the where clause is always based on just that local variable.
On the local variable, yeah.
What was it doing? A table scan?
In that case, a table scan, because the query optimizer has no idea during the query compilation which value you are providing here. So as I've said earlier, in that case, the query optimizer uses the density value. In our case,
use the cached plan.
the cached plan is still reused, but the density value is used to generate the initial plan. Means in our case, our initial estimation is 750 rows. With that estimation, we are over the tipping point. Means SQL Server has chosen here an execution plan. Where we have it. SQL Server has chosen here an execution plan with a bookmark lookup. With a table scan, sorry. But the plan is still cached and reused. Okay?
So if I had a index covering, for example, a date,
Yeah.
and I had a local function saying get last business date or something, it would never think of using a plan based on an index covering the date.
Well, when you have a covering index for such a query, all your problems are just gone away. Because you have no bookmark lookup with a covering index. As we have also already seen earlier. The problem itself is very easy to solve. Create a covering index. The covering index eliminates your bookmark lookup and you are happy. All your problems are just gone.
Except you've now got 40, 50 indices on a table.
Then you have a huge problem, of course, as I've also said. When you add a huge amount of non-clustered indexes, you are just degrading your write performance. But the solution is very simple. The solution is very simple. So using with local variables, it's not really the preferred way because it depends on the density of your data which execution plan SQL Server generates you. What you can also do, you can tell SQL Server, I want to recompile every time that stored procedure when I execute it. It means when you recompile that stored procedure every time, you always get a new execution plan, which is always optimized for the current provided input values.
But why would you choose to do that as opposed to say, since this is obviously your own stored procedure and you can put it with recompile, why would you put it with recompile when you can put it optimized for UK country code, for example?
Because with optimize for, you have to know very, very well your data. Imagine I'm telling you Austria is a great company, and next week you are running a marketing campaign in Austria. You're getting 10,000 new customers. In that case, your data distribution is changing, but when you're using a query hint, you are not giving the query optimizer the allowance to give you a new, better execution plan. Therefore, when you are working with query hints, you have to know your data, and you also have to know when your data changes. Because you are mainly overwriting the brain of the query optimizer. So now, with the recompilation of the stored procedure, we just get a new execution plan every time when we execute that stored procedure. Value of 1 record, bookmark lookup. Value of 2, 1499 records, table scan. The problem is, a recompile of the complete stored procedure is not the best thing. Normally, stored procedures contains a huge amount of different SQL statements, and maybe you have only in one specific statement that parameter sniffing problem. Here, with the recompile, SQL Server recompiles the complete stored procedure, every statement. So you're again wasting a huge amount of CPU cycles. What you can do is you can also make a so-called statement level recompilation, available since SQL Server 2005. Means in that case, SQL Server just recompiles that specific statement every time when you execute it. For all the other statements, we just generate once our execution plan, we cache that plan for that statement, and afterwards we just reuse that cached plan. Normally, when you can't change your indexing strategy, that's the preferred way how to deal with that problem. You just recompile that specific statement that causes you that parameter sniffing problem. So in that case, when we run that stored procedure, we get 2 times in the execution plan a bookmark lookup. Because the value of 1, very, very selective, just appears once in that table. Afterwards, when we rerun that cached execution plan with the value of 2, the first cached plan gets just reused. So here we still have the same problem with an estimation of 1 row. In reality, we are getting back 1499 rows. And the second statement was just recompiled. Means in that case we are again over the tipping point, and now we have the table scan, which is the preferred way for the value of 2 to retrieve that data. And as you can see, when we go here to the select operator, you can again, no, we don't have here the parameter list. Maybe we have it here in the first one. Yeah, here in the first one, you still see that the compile time and runtime values are just different. So that's the preferred way in combination with stored procedures when you can't work on your indexing strategy. The default one should be always to create or to try to create a covering non-clustered index.
So is there nothing you can do on this statistics? You can't use a histogram or something to tell that for this column there really is a strong skew on the distribution?
No.
You can't?
Yeah. because the initial plan is just based on the first provided input parameter value. Of course, the same problem can happen when your statistics are inaccurate. You have an estimation of one row, and in reality you are getting back for that value of 1,000 rows. The same problem. The same problem can happen with inaccurate statistics. We have the optimize for query hint. As I've already said, you really have to know your data, and you have to know when your data changes and how your data changes. In that case, we are telling the query optimizer, I always want to have a plan which is optimized for the value of 1, regardless of which parameter value we initially provide. So we're already working here with the sledgehammer against the query optimizer of SQL Server. We are telling the query optimizer, hey, we are smarter than you. So when we run that execution plan, that start procedure with the value of 2, normally you are expecting a table scan because you are retrieving a huge amount of data. In that case, we have a bookmark lookup. And again, the estimation is just 1 row because we have optimized that execution plan for the value of 1. Means again, the bookmark lookup was done over and over and over again. And you can also see at the select operator, our compile time value is 1. Because that's the value for which that execution plan was optimized for. And in that case, we have 1,505 logical reads. The complete scan of the table costs us 4 logical reads. Just think about that. You can also optimize your stored procedure for unknown. You have no idea for which parameter value. In that case, when you optimize for unknown, then SQL Server again just uses the density value that we have seen previously. Means in our case, with optimize for unknown, we have an estimation of 750 rows. 750 rows are over the tipping point, means we are just scanning again the complete table. So optimize for unknown also not really a good idea. You don't know your data, the query optimizer knows anything. So I'm not really a huge fan of those query hints. Optimize for. The option recompile on the statement level can be quite interesting. Imagine now we have our original stored procedure. And we can't change that stored procedure, and we can't work on our indexing strategy. Imagine you have a third-party application, that third-party application executes a problematic statement, but you can't change anything. What you can do in that case, you can create a so-called plan guide. A plan guide is a native database object, and with a plan guide, you are able to attach a query hint to a specific statement. Every plan guide has a name, is for a specific statement, for example in a specific stored procedure. Also works with just statements that you are submitting. And in that case, you can provide a query hint. You can attach transparently a query hint to a specific statement. For example, an option optimize for, or we can also use the option recompile that we have seen previously. So in that case, we just tell SQL Server, we want to recompile that statement of that stored procedure every time when we execute it, without changing the stored procedure itself. So when we run that plan, value of 2 gives you a table scan, value of 1 gives you the bookmark lookup, without changing the stored procedure. As I've said, the plan guide itself is just a native database object. Means when you do a backup, restore of that database, you also have the plan guide. Of course, you shouldn't overdo it with plan guides because you can influence here in a transparent way the query optimizer. Imagine you do here an option optimize for, you get a completely different plan and you have no idea why. So in that case, you can also fool your colleagues with plan guides. So you should not overdo it. But that's one way how to deal with some specific problems when you are not allowed to change your indexes, when you are not allowed to change the implementation of statements or even stored procedures. We haven't changed here anything, we have just created a plan guide, a database level object, and influenced indirectly the query optimizer. And with SB control plan guide, you can finally drop it when you don't need it anymore. Questions on that?
Since what version of SQL Server have you been able to, in plan guides, attach a hint to a specific SQL Server statement?
At least since SQL Server 2005. Other questions so far?
Again, at the right time, if you can change the indexes,
Yeah?
but can't change the SQL statement, your initial example about country code, could you create a filter index that could say exclude the United Kingdom and leave in Austria and other relatively small ones? Would that solve that problem?
No, not really.
Ah.
No. Because in that case, the query optimizer will not use the filtered index.
Really?
Yeah, with a parameter value.
Ah.
Because when you afterwards cache the plan, you would get back a wrong result.
So only work with hard-coded values, not with...
Only with hard-coded values, yeah? Because then you can predict the result. So when we go up to that non-clustered that we have created somewhere, and we create a filtered index where column 2 equals 1, and we recreate that non-clustered, and we recreate our stored procedure and we execute it, the non-clustered is not used. Because you would only get the correct result with the input parameter value of 1. With the input parameter value of 2, if you cache that plan with the filtered non-clustered, it would give you an inaccurate result. 0 rows, but in reality you have 1499 rows. So in that case, the filtered non-clustered only works with hard-coded values. So when I say here, select star from that table where column 2 equals 1, then we have the filtered. And with the value of 2, you have again the table scan.
Interesting invitation.
Yeah? But it makes sense. It makes sense. It's the same when you're hinting here SQL Server with that non-clustered. The query optimizer isn't able to produce you here an execution plan anymore. Because it would give you a wrong result, no rows, but in reality you have rows. So before the query optimizer gives you a wrong result, the query optimizer says, hey, sorry, I'm not able to produce you here an execution plan. Because that's a contradiction that we have here. We can't have any rows with the value of 1 in that filtered non-clustered. This doesn't work. Okay? Good question. Let's talk now a little bit more about parameterization. As I've already said earlier, the same thing can happen when you're working with parameterized SQL statements, when you're working with ADO.NET, Entity Framework, some other OR mapping technologies. The same problem will just happen because you initially generate a plan with a parameter value, you cache that plan, which is optimized for the first provided input parameter value, and then you just reuse it. Same thing. The problem that we have in SQL Server is that SQL Server also can auto-parameterize specific SQL statements. We have a so-called auto-parameterization and a so-called forced parameterization in SQL Server. When we have in SQL Server a so-called safe plan, then SQL Server will auto-parameterize our SQL statement. So it means you provide a hard-coded parameter value and SQL Server substitutes that hard-coded parameter value, or that hard-coded value with a parameter value. Safe plan means that you get, regardless of your input parameter values, the same execution plan. Means when you have a bookmark lookup in your execution plan, you have no safe plan anymore. Because, as we have already seen, based on the input parameter value, you can get different execution plans. Bookmark lookup, table scan, or clustered index scan. With auto-parameterization, we have a huge amount of restrictions. So, for example, when you make a join between two tables, SQL Server can't auto-parameterize your SQL statement anymore. When you use an in, when you use a union, a distinct, stop, and so on, SQL Server can't auto-parameterize that anymore. Therefore, we have a database option. Forced auto-parameterization means we can tell SQL Server that SQL Server should auto-parameterize almost all of our SQL statements. Means when we enable forced parameterization, we just have a few exceptions in which SQL Server can't auto-parameterize our SQL statement anymore. Of course, when we are setting a forced parameterization, we again have to know our data and we have to know our execution plans very, very well, as you will see. I create here a simple stored procedure. With that stored procedure, we just analyze the plan cache. So what I'm doing here, I'm just going to the plan cache, system exec cached plans. I retrieve the execution plan, the SQL statement, and also the query statistics that we have already seen previously. So just a simple stored procedure which helps us with the analysis of the plan cache itself. Okay? And I create now a simple table. Let's clear the plan cache. And I have here a simple SQL statement with a hard-coded parameter value. And as you can see, with that hard-coded parameter value, whoops, that was wrong. With that hard-coded parameter value, SQL Server was able to substitute that parameter value with a parameter. That's auto-parameterization. That's auto-parameterization in SQL Server. Means we have an auto-parameterized plan. That plan gets cached and can get reused with different hard-coded parameter values. Means when you use here a different value, SQL Server can reuse that plan. That's auto-parameterization. Of course, that can get, again, very, very dangerous when you have bookmark lookups. When we look into the plan cache, you can see now that we have one auto-parameterized plan here with a data type numeric 3-2. The crazy thing here is about SQL Server. As you can see, SQL Server chooses as the parameter value the smallest possible data type. Means when we rerun that query with a larger value like 124, which doesn't fit in a numeric 3.2, you get a different parameterized version of that query with a numeric of 5.2. Just think about that. That's a side effect of auto-parameterization. When you use a 1200, we have another version of that plan with a numeric 6.2. So that's a very interesting side effect of auto-parameterization. Show you here another thing. What I'm doing here, I create a copy of the sales order header table. And I create on the customer ID column a non-clustered index, and I'm changing the data distribution. I'm just saying the first 60,000 rows of the table are just belonging to one customer. So we have just a different data distribution. One customer has very, very huge amount of orders, other customers have a small amount of orders. Just an uneven data distribution. Means when we run that query, by default, SQL Server gives us here a table scan because we are over the dipping point, because we are retrieving here 16,000 rows out of 31,000 rows. SQL Server was also not able to auto-parameterize that query because it's not safe to auto-parameterize that query, because with a different input parameter value, you get a different execution plan. So as you can see, almost two identical queries, two different execution plans. In that case, SQL Server isn't auto-parameterizing your query because it's not safe. So that's one of the largest problems that we're seeing in SQL Server. You have two almost identical queries which just have a different input parameter value and two different versions of an execution plan, because you have no plan stability. Means you can't predict performance, because you can't predict which execution plan you get first. Which execution plan you get depends on which input parameter you are providing first. Just think about that. Another input parameter value, also very, very selective result. Again, we have our bookmark lookup. When we look to the plan cache, you can see we have those three unparameterized queries. So by default, when you have bookmark lookups, the auto-parameterization of that query isn't working because it's not safe. It's just a safety net by SQL Server. But we are able to enforce that parameterization. By default, the parameterization is set to simple, the behavior that we have seen so far, and we can also force SQL Server to perform that parameterization with some serious side effects. I run the first query, not really selective, 16,000 rows out of 31,000 rows, table scan. But now, SQL Server has auto-parameterized that plan, means we have cached that execution plan, which produced 780 logical reads, and now with all subsequent queries, we just reuse that cached plan. Now we have an estimation of 16,000 rows. In reality, we're just return one row, means we're scanning the complete table with 780 logical reads. Previously, that query was very, very fast with just 3 logical reads. Okay? The crazy thing here is, imagine we are running those statements in a different order. The first step, your selective query, just 1 record. SQL Server gives you a bookmark lookup, 3 logical reads, and then you reuse that cached plan with a non-selective input parameter value. Again, you're doing the bookmark lookup over and over and over and over again, and that query costs you 16,000 logical reads. You can't predict performance anymore, because it depends with which input parameter value your users are first executing that query when you have restarted SQL Server. Just think about that. The same can happen when you perform a cluster failover. The performance depends which input parameter value you are providing first. If you are lucky, you are getting a table scan, because the table scan is always the same slow. If you are unlucky, you get a bookmark lookup and your performance will exponentially go slow. So as you can see, bookmark lookups, they are really, really dangerous. Crazy things can happen with them.
Is there any tools available for us to identify those scenarios?
Out of the box, no. As I've said earlier, mainly you can work with the dynamic management view, system exec query stats. Also, when we take that plan, every plan in SQL Server has a so-called query plan hash, which is again a hash value which uniquely identifies that execution plan. So we can go to system exec query stats and restrict on that query plan hash so that we have the statistics of that specific plan in front of us. And as you can see here, when we go to the right, you have here your min and max logical reads. Very, very large variation, so you should further have a more detailed look on that plan. You can also see it from the row count, min, max rows. Once we just retrieved 1 row, once we retrieved more than 16,000 rows. You can also see it from the elapsed time. Minimum 21 milliseconds, those are microseconds. Maximum elapsed time with the bookmark lookup, we had here 333 milliseconds. You can also see it from the execution time, because the bookmark lookup is just done over and over and over again. It's just a for each loop, for every record. That's the main problem. Therefore, the bookmark lookup isn't really scaling very, very well. Questions on that so far? Okay, and for the final part of that presentation, we will talk about deadlocks. Because that bookmark lookup can also result in a deadlock situation when you have a parallel write activity on that plan. Let's demonstrate that. Imagine we have one plan with that bookmark lookup. So we have the seek, we have the lookup with our nested loop, and we have a second plan which changes the non-clustered index. In that case, we perform maybe a SQL operation to find the rows that we are changing. Then we compute the new values. And imagine we have an update statement which changes the clustered key value. In that case, we have to change our clustered index, and because the clustered key value is also part of every non-clustered index, SQL Server also has to update the non-clustered index. And if both plans are running at the same point in time, and if the timing is perfect, you get a deadlock between both. Imagine what happens. Imagine with a session ID 52 and 52 reads from that non-clustered index, we acquire here shared lock. In the next step, we have here our update plan. Let's say with a session ID of 55, and we change our clustered index. In that case, we acquire an exclusive lock. The next step, our read query continues, and session ID 52 tries to acquire a shared lock for the bookmark lookup on the clustered table. Do we get that shared lock? No, because we are blocked by the exclusive lock. Means session ID 52, our select statement with the bookmark lookup just waits. Then our update plan continues, and session ID 55 acquires an exclusive lock on the non-cluster. Do we get that exclusive lock? No, because session ID 52 has a shared lock on it. Means we are waiting. Every query waits on the another one. Traditional deadlock. Very simple to solve. Create a covering non-clustered index. Let's demonstrate that. Nice thing, it's very easy to reproduce. I have here two sessions. Let's create a simple table. And I have here a simple query, for example, which updates our clustered key value of call 1. In that case, when we run that statement, when we look at the execution plan, you can see SQL Server has to update the clustered index, SQL Server has to update the non-clustered. Same that I have shown you here. I have a second query where a select statement just produces a bookmark lookup. When you're running both statements separate from each other, everything is fine. What I'm doing now, I'm just running those statements in a while loop. And I'm helping SQL Server a little bit by setting the transaction isolation level to repeatable read. Repeatable read just means we are holding those shared logs a little bit longer till the end of our transaction. So I'm just helping SQL Server to make it easier to reproduce that deadlock. When you have a production environment, you can even have a bookmark lookup deadlock in the default isolation level of read committed. I'm just helping here SQL Server in both sessions to make it easier to reproduce that deadlock. We run continuously our write workload. In the second session, we run continuously our read workload. Takes a few seconds. And as you can see, first session, the update statement was rolled back because we have a bookmark lookup deadlock. Just think about that. Very easy to solve. Create a covering non-clustered index for that query. In that case, you don't need to go to the clustered table to perform the bookmark lookup, and your deadlock is just gone. Very simple. So when we change now our indexing strategy, and we include, let's say instead of a select star, we just do a select call to, and we include call to in the leaf level of the non-clustered. Then we get read of that bookmark lookup. we just perform an index seek non-clustered, means again we can run both transactions forever without any deadlock anymore. So that's the first option when you can work with your indexing strategy. The second thing is you can enable optimistic concurrency. For example, read committed snapshot isolation, which was introduced back with SQL Server 2005. With read committed snapshot isolation, select statements are not acquiring shared logs anymore because they are reading transparently the corresponding version from the version store, which is held in DempDB. So when you can't work with your indexing strategy, you can also use read committed snapshot isolation, and that specific kind of deadlock will be also gone away. So 2 ways how to deal with that specific problem. And as you can see, we still execute without any deadlock. So the deadlock was just caused by that bookmark lookup operation in the execution plan. Just think about that. One specific pattern in an execution plan produces a huge amount of different problems. So, the first step, we have talked about bookmark lookups, why they are needed in SQL Server, how they look like in the execution plan. Then we have talked about the tipping point. As you have seen here, most important thing about the tipping point is the tipping point just depends on the number of pages you are reading, not on the number of records. Then we moved on to parameter sniffing, which is one of the largest problems or challenges in SQL Server when SQL Server caches a plan, which is optimized for the first provided input parameter values, and then we're just reusing that plan. It can cause you a huge amount of different problems. We have talked about auto-parameterization, forced parameterization. As you have seen, forced parameterization also not really recommended because SQL Server will just reuse a parameterized version of that plan, and this can also cause you a huge amount of performance problems. And finally, as you have seen, with a bookmark lookup in the execution plan, it's very, very easy to get a deadlock when you have a concurrent update execution plan, which also changes your clustered and non-clustered index. Questions so far?
Yeah, if you've got a stored procedure and SQL Server's cached the plan,
Yeah.
and you see that it's using the bookmark lookup,
Mhm.
you then subsequently go and create a covering index
Yeah.
for it. Will that plan then detect that index automatically?
Yeah, because you are changing your database schema and therefore SQL
Right.
Server triggers
So
a
it will be-
recompilation. Same
Right.
thing happens when the statistics are updated.
So at any, right, so execution plans are then changed.
Yeah.
Any change to the schema then triggers that?
Yeah, yeah.
Right, okay.
On all dependent tables, of course. When you are creating or changing an index on a different table, then your execution plan is just reused. But SQL Server recompiles every time when on the corresponding table a schema change has happened or when your statistics are updated. If you want to know more about performance tuning and troubleshooting in SQL Server, I'm coming back to London in the first week of June, a 5-day-long workshop just about performance tuning and troubleshooting in SQL Server. You can find more information about that workshop on my website at sqlpassion.ad, and as I've already said, when you give me a business card, I can also grant you a discount of 10%. Okay, so thanks for attending. I have again today another session in the afternoon at 4 o'clock where I will talk about unique identifier values as primary key values, which is also a very, very interesting and controversial topic in SQL Server. So thanks and see you later. Okay, in my first talk today, I want to talk about the dangerous beauty of bookmark lookups in SQL Server. Who of you has already an idea what a bookmark lookup in SQL Server is? Okay. Who of you has already attended a session of mine yesterday? Okay, so I don't introduce myself anymore. You already know everything that you should know about me. What's the agenda for the next 90 minutes? The first step, I want to talk what a bookmark lookup is in SQL Server, why SQL Server needs a bookmark lookup so that everyone has a common understanding about bookmark lookups, and then I just want to show you different problems that can occur in SQL Server in combination with execution plans that contains bookmark lookups. We will talk in detail about the so-called tipping point, about a problem in SQL Server called parameter sniffing, inaccurate statistics, how SQL Server deals with parameterization in combination with bookmark lookups, and in the end, if time permits, I also want to talk about some specific kinds of deadlocks that can also occur in SQL Server in combination with bookmark lookups. So mainly, I'm just talking about the various problems that bookmark lookups can have in SQL Server. A bookmark lookup means that the query optimizer has chosen in the execution plan a non-clustered index, means we are reading the requested data from that non-clustered index, and finally we retrieve in our select list additional columns that are not part of that non-clustered index. Means we get some records from that non-clustered index, and afterwards SQL Server has to retrieve the additional requested columns for every record that we have retrieved from that non-clustered index. And when we look here at the execution plan, you will see that SQL Server performs here at date. The column modified date is not part of that non-clustered index, means for every row that we are returning from that seek operation, SQL Server has to perform that key lookup on our clustered table. Means we execute that bookmark lookup 19 times for every row that we return from the index seek operation. You can see again from the output list, we request the column modified date. As you can see, for that simple query, we already need 42 logical reads, means SQL Server read here 42 pages of 8 kilobytes. Another query, just the same thing, we return 8 records. In that case, we perform that bookmark lookup 8 times, number of executions. We have here 18 logical reads. As I've said previously, such a bookmark lookup in an execution plan can be eliminated very easily. You can see that we retrieve the column modified date with the bookmark lookup, means we can create an additional non-clustered index which includes that column modified date in the leaf level of that non-clustered index. Means when we create that non-clustered index, SQL Server is finally able to satisfy the complete query from that non-clustered index. Means we're just eliminating that bookmark lookup. So let's create that one. Okay. Let's create that one. When we finally rerun our query again, you can see SQL Server has chosen that newly created non-clustered index. So there's no need anymore to perform that bookmark lookup, because every column that we're referencing in our query is now part of that non-clustered index. Means in that case we have only 2 logical reads instead of 18 logical reads. So that's already a huge difference.
Was that the table with the clustered index?
Bookmark lookup operation means for every record that we retrieve from that non-clustered index, SQL Server accesses our table, our clustered index, over our heap table, and just retrieves the additional information. When we deal with a bookmark lookup, we have two kinds of bookmark lookups in SQL Server. We have a so-called clustered key lookup. That kind of bookmark lookup is performed by SQL Server when we deal with a clustered table, so a table with a clustered index. If we deal with a heap table, a table without any clustered index, then we have a so-called row identifier lookup in our execution plan. As we will see later, we can eliminate bookmark lookups very, very easily in SQL Server by creating a so-called covering index. A covering index in SQL Server is just a traditional non-clustered index which contains all the columns that we are requesting in our query. So normally when you have a query in front of you, you should add the columns on which you are restricting in your where clause into the navigation structure of that non-clustered index so that you can perform seek operations, and every additional column that you are referencing in your select list, you should include in the leaf level of that non-clustered index. Means when we are including those additional columns in the leaf level of the non-clustered index, we can eliminate that bookmark lookup in the execution plan. Of course, when we include additional columns in the non-clustered index, we just create a redundancy of that data. Means those columns are part of our table, of our heap table or clustered table, and those columns are also part of that non-clustered index. Means when we are changing that column, we are degrading our write performance because SQL Server has to change that column twice. Once in our table and also once in the non-clustered index that we have created previously. That's also the problem of indexing. On one hand, you're improving your read performance, and on the other hand, you're just degrading your write performance. Let's have a look on that. I have here a simple query which retrieves the record with the database log ID of 15. It's a heap table, a table without a clustered index. As you can see, we have on the column database log ID a non-clustered index. That non-clustered index is referenced in the execution plan, so SQL Server makes a seek operation on that database log ID column, as we can see from the seek predicate. And the problem that we have now with that query, we select the column database log ID and also the column database user. That column database user is not part of that non-clustered index, means SQL Server has to perform a lookup operation on our heap table. And as you can see from the output list, we request here the column database user. Means from the execution plan, a bookmark lookup is always performed with a nested loop operator. Means for every record that we get from our non-clustered index, SQL Server has to perform that bookmark lookup into our table. Means the more and more records that predicate returns you, the more often you have to perform that bookmark lookup. In that case, we just return one row, means we also have to perform that bookmark lookup just once, as you can see here from the number of executions. I have here another query which performs a bookmark lookup on a clustered table. As you can see, we request here a range of email addresses from the table person.email address. As you can see, that seek operation returns us 19 qualifying rows. In addition, we want to request the column modified.
So it chose to use that.
Yeah. In that case, Query Optimizer has seen, hey, every column that you are referencing in that query is part of that non-clustered index, so we just read that data from the non-clustered index. Of course, when we update that column modified date very, very often, that non-clustered index just degrades our write performance. Because now when you're changing that column, you also have to change that column twice. Once in the clustered index in our table and once in the non-clustered index. So when we run here a simple transaction and we say update person address set modified date equals get date where address ID equals 42, and we run that transaction, and when we look at the execution plan, you can see we have a clustered index update operation, and SQL Server also has to update the non-clustered that we have created previously. Because with the included column, we just have created redundant data in that table. We are storing that column modified date physically 2 times. Once in the clustered index, once in the non-clustered index. So as you can see here, we need for that query 4 logical reads. When we drop again that non-clustered index and we run the update query again, it will be faster. No, not really. It's just a small table. But when we look at the execution plan, no, this was the wrong one. This one. So now we should be faster. Yeah. Now we just have 2 logical reads, so our write query is just faster. As you can see, we are just updating our clustered index, no non-clustered index. Of course, our read query or select statement is again slow. That's the problem of indexing. On one